Hey everyone, this is Michael from the Data Incubator. I'm the founder here, and we're really excited to have Brian with us. Wave. So this is Data Science in 30 Minutes. We're going to be doing a little bit of data science and showcasing what we can do in 30 minutes. So as you are listening, if you have any questions, feel free to sort of Slack them out, or send them out on the prompt. I think if you look at your Google Hangout and you sort of mouse over to the left, you'll see a little blue chat icon. Just open that up and feel free to ask us any questions you might have. And feel free to ask them as we go along. I think for the purposes of maybe keeping this simple, we'll wait until the very end and answer them then. I'm really excited to have Brian here with us. So Brian is a data scientist at Capital One, and he was also a fellow in our spring cohort in 2015. So prior to this, prior to joining the Data Incubator, he was a postdoc in computational astrophysics at Columbia and NYU, and worked on simulating environments around binary black holes. So he received his PhD in physics from the University of Illinois, Urbana-Champaign, and he's going to be talking about reinforcement learning and some of the interesting stuff that he has been up to since he left the incubator and is now at Capital One. So Brian, you want to take it from here?
Sure. All right. Thank you, Michael. It's good to be back here. Feels like it's been a long time, but it's good to see familiar faces. So let me switch to the screen share. I think it's this one. Yes. Okay, there we go. All right, so I'm going to be talking about reinforcement learning. I'll also be talking about what's called multi-arm bandits, which I consider to be a subset of reinforcement learning. That's kind of a semantic issue, but for the purpose of this talk, we'll say that it is. And I'll explain what that means in a second. So let's start off with this quote from probably the most popular book on reinforcement learning by Sutton and Bartow. So a gazelle calf struggles to its feet minutes after being born. Half an hour later, it's running at 20 miles an hour. So this is a cool quote because, first of all, it's amazing that that's possible. And it kind of speaks not only to the challenge of reinforcement learning and sort of how these algorithms work, but it also tells you a little bit about the lineage of this field of study. So reinforcement learning kind of grew out of the study of animal behavior in the old days, and it kind of merged with computer science at some point, I think in the 70s perhaps. So in the animal behavior world, it's this idea that animal behavior is sort of trained through systems of rewards and punishments. You can imagine like Pavlov's dog, that sort of thing. So the idea is reinforcement learning is a set of algorithms that we use. The modern viewpoint is it's a set of algorithms where when you don't have, it's distinct from supervised learning in the sense that you don't have like a training data set like we're used to. And you have an agent that is living in some world and it's responding to feedback and rewards and modifying its strategy for the actions it can take based on that. So I'll make that a little bit more rigorous in a second, but first let's give an example here. Probably the most famous example from the news recently is Google's Alphago algorithm. So Go, for those who don't know, it's an ancient Chinese board game. Its rules are relatively simple, but I think the number of possible games is larger than the number of atoms in the universe, something like that. So it's much more challenging than chess, actually, to design an AI that can beat a human at Go. And this had not been done until this year. Google's team called DeepMind an algorithm that they call Alphago, and it beat the world champion. I forget do you remember the 4 out of 5 games, something like that. So this was considered a big breakthrough. And they were doing what's called deep reinforcement learning. So it's a reinforcement learning algorithm with a deep neural net sort of baked in as well. So I think there's a lot of attention today in reinforcement learning. It's kind of a hot and growing topic. It's perhaps still on its way up. It's So I don't know, I thought it would be a fun thing to talk about. It's something that's a little bit outside the box from what you might normally hear about in the world of data science, but I think it's definitely, you'll be hearing more about it in the coming months. Okay, so let me just define some terms. So the goal of reinforcement learning is you first define your agent. So this is usually yourself or your company or whatever. It's the thing that you're trying to optimize outcomes for. So this agent lives in what we call an environment. And the environment you can think of as a set of possible states that the agent can be in. And it moves from one state to another by taking actions. Based on the actions that the agent takes, the environment can give the agent rewards. So what you're trying to do is derive a policy, which is basically a mapping from states to actions. So another way of saying that is you want to come up with an optimal, you could even imagine tabulating it if it was a simple case. For any state you're in, what's the best action you can take? Which state should you try to move into? So this diagram that I have here kind of illustrates this. So the agent takes an action, tells that action to the environment gives it a reward and puts it in a new state, and then you basically repeat. And what you're trying to do is you add up all these rewards, and you want to find the optimum sort of cumulative rewards as you play this game. So that's a little bit formal and abstract. Let's see. I already said this a little bit, but just to emphasize. So supervised learning, so typically we hear about supervised learning and unsupervised learning. This is maybe somewhere in between because you do gain information as you run through the algorithm from the environment, but starting at the initial state, you don't have a supervisor, you don't have a training set. So in the gazelle example, when the gazelle is born, its brain does not have a set of rules in it for what muscle to activate when it steps on a rock or something like that. It just very quickly learns from getting feedback as it falls over when it takes the wrong step, that sort of thing. So let's run through some other examples because I think we've been a bit abstract. So robotics is a huge area where you see reinforcement learning. So if you have a robotic arm, you can imagine that the environment is the set of positions the arm can be in. And the actions you can take is to bend the elbow, close the hand, etc. And then you get a reward when the robot opens the refrigerator or whatever it's trying to do, right? So the policy ends up being like sort of the robot learns how to efficiently open refrigerators, and that strategy is the policy. So other things we already talked about, Go. Another classic example, going back to sort of the animal behavior thing, is a mouse learns how to navigate a maze by getting a cheese reward at the end of the maze, right? So for each state in the maze, it can go up, down, left, or right, perhaps, and it learns which of those actions to take to get its cheese. So some more business-oriented examples, a credit card company might have, so I put credit card company because I work for Capital One, but there's a published paper from IBM actually for New York State used reinforcement learning to optimize its tax collection strategy. So when someone doesn't pay their taxes, there's a set of things the state can do, and learning an optimal policy for when to intervene and how often, that sort of thing, you can learn that. And then ad tech uses a special case of this, which we'll get to in a second, the multi-arm bandit problem, very often it's kind of like a souped up A/B testing. Basically optimizing click rates by placing ads. Web design is similar. We won't talk about call centers. But so the point is there's a lot of applications for this, and you'd be surprised how many problems can be approached this way. So an important concept here that we should discuss is exploration versus exploitation. And this is kind of very well illustrated in the multi-arm bandit problem, which we'll talk about next. But the idea is basically when you don't have a supervisor, you're trying to kind of create your own supervisor in a sense. So the gazelle is learning information as it learns to walk, right? It's trying things, succeeding or failing and increasing its knowledge of the environment. But it doesn't want to necessarily just experiment and figure this out. It also wants to run as quickly as possible. So that's exploitation. So there's usually not a correct way to do this trade-off. It kind of depends on your business goals. There's always going to be an inherent trade-off between exploring and exploiting the knowledge that you currently have. So let's talk about multi-arm bandits. So this is kind of a weird name. What it comes from is sort of a colloquial term for slot machines. Apparently is a one-arm bandit. I had not heard this before, but apparently people call them that. The idea being it's got one arm and it just steals your money. So a multi-arm bandit is, imagine you're an octopus, I guess, and you're standing at a slot machine with a number of different arms, or maybe a few slot machines in a row. And each one of these arms may pay out at a different rate. So if you knew which one paid out the most, you would only pull that arm, right? But we're imagining that you don't know anything about which arm is best. So you need to basically sample all the arms in order to gain wisdom about which arm is the best and then start exploiting it. So this perfectly illustrates this trade-off between exploration and exploitation. Because remember, so the payout is still statistical. So it's not like you can pull it once and know. You have to pull it. The more you pull each arm, the more you learn about it. But you want to start reaping the rewards of any knowledge you have as soon as you get it. So what algorithm can we come up with for most effectively playing this multi-arm bandit? So it turns out there's a lot of different ways to do this, but the simplest way to handle this trade-off is what's called an Epsilon greedy algorithm. So a purely greedy algorithm would mean that basically at any time, whatever arm you think is the best, you pull that one. So if you pull one arm the first time and it gives you some reward, then you'll just never try any of the other ones, because as far as you know, that's the best one at this point, and you'll just keep pulling it. So as you can imagine, that's probably not the best thing you can do. But if you happen to be right, then it is good because you don't waste any pulls on other ones. So what people usually do instead is what's called epsilon greedy. So epsilon of the time, a fraction epsilon of the time, you just pull a random arm. And that's how you handle your exploration. But then a fraction 1 minus epsilon of the time, you make the greedy choice. So epsilon is usually some small number. But I can't tell you what you should use for epsilon. It kind of depends on, again, on your business problem. So let's look at an example. So this is just a kind of a flow chart. You can see here, it's basically what I just said. All right, so let's look at this coded example. So what we're doing here, we have our little bandit class. And so when we initiate it, we're going to give it 10 arms, and each one is going to have its payout rate, which is going to be normally distributed with a mean of 0, sigma of 1. Okay? And then we're going to keep track of how many times we pulled each arm. That's what this K is. And we're going to keep track of our estimate for these are the actual arm values. Then we're going to keep track of the estimated arm values. Each time that we pull the arm, it'll give us a reward, which will have a noise component, which is also a Gaussian distribution with a sigma of 1. And then this is our strategy, this epsilon greedy strategy, where we choose what we think is the best, 1 minus epsilon at a time. We randomly choose the rest of the time. And this is just where we update our estimates, and take my word for it that this just keeps a running average for each arm of the rewards we've gotten in the past. So here's, we won't go into the details of this. This is just a little experiment function that runs this n times, or n pulls times, which we're going to set to 3,000. And since as you saw, there's a lot of noise in these things, so we're going to do this experiment 500 times and then plot the results. So it's running right now, but this is what it's going to give us. So we're doing this for a few different values of epsilon. And as you can see, when epsilon is 0, that's purely greedy. So it's just going to always give us the same average rewards. And then if we increase epsilon to 0.01, it takes us a while to do better. But eventually, there's some noise here, so it's hard to see, but this 0.01 does best in the end. 0.1, epsilon 0.1, you're exploring more, so you asymptote more quickly, but you won't do quite as well in the long term because you're still wasting these testing polls on your exploration. So which one is the best? I can't tell you. I mean, if you're going to run this for a very long time, then maybe you want a large epsilon, or a smaller epsilon, because eventually you'll asymptote to a higher value. But if you're not going to run this campaign, ad campaign or whatever this is for very long, maybe you want a larger epsilon so you can get that exploration done quickly. So that's how this trade-off works. So, wow, time is going really quickly. So I have a cool Twitter example that I want to show. So let me do this too. This is the same thing, but just to make this a little easier to visualize. So this is an example. I won't go through all the details just for time's sake, but you can look at this later. I'm skipping around this notebook a little bit, so take it as a reference. But so for the way this maps to like ad tech is, you imagine that each arm is like an ad that you can place. And so you have these ads and you don't know which one's going to have the best click rate. So rather than doing an old-fashioned A/B test, which takes money and time and effort on the part of data scientists, you can automate this and make it more efficient by having multi-arm Bandit just sort of naturally figure out which is the best one by both testing and exploiting at the same time. So here, instead of placing ads, what we're doing is we're kind of betting on out of tweets that are streaming. So this is streaming right now. Tweets that have the word election or president in it, we have a Hillary Clinton ad, a Donald Trump ad, or a Bernie Sanders ad. So we place one of these ads, and if the tweet contains those words in it, then that's like a click. So what you can see, unfortunately, this tends to always happen when I run this. Donald Trump runs away with it very quickly. So what we're seeing here is the value is the estimated fraction of these tweets that have Donald Trump in them, or Hillary, et cetera. And then K is how many times we tried. So you can see Donald Trump is winning, and hence we are serving the Donald Trump ad more often because we believe that is worth more. But every now and then we still are testing the other ones because this is an epsilon greedy. So just because this looks cooler and is more fun, I also want to show what's called the randomized probability matching approach. Oops, stop this. And this is the same idea. It's just instead of epsilon greedy, you take a Bayesian approach and you actually have a distribution for this click rate, and then you're constantly updating. So you set a prior, and then you're constantly updating the posterior for that click rate. So you can see that the blue curve is the distribution for the click rate that we estimate for Donald Trump. And because it is farther to the right, we're going to play that more, which is why you see it moving more often. And what we do is basically each time we compute the probability that we sample from each distribution, compute the probability that a given ad is the best ad, and then with that probability, use that probability to decide which arm to pull next. So that might take a little bit to digest, but you can look at the code there, and it will make a little bit more sense. So that's kind of fun. And this is also called Thompson sampling. So I use the word strategy for sort of deciding how you decide which arm to pull. So one strategy is epsilon greedy, another one is Thompson sampling, and there are other ones as well. You can kind of do whatever you want. You can, for example, do epsilon greedy, but then lower epsilon once you start to zero in on what you think is a good choice. Sometimes that's good, sometimes it's not. Let's scroll back up real quick. One reason why you might not want to update lower epsilon. So I showed you this example before. This is an extension of that. I don't actually have code to generate this, but So here what we're doing is imagining that the intrinsic value of each arm actually changes dynamically. And this is also very common with ads, for example. You know what, maybe one day people like Capital One's Jennifer Garner ad, but then later they prefer Samuel L. Jackson. And if that's changing constantly, you don't want to necessarily stop your ad campaign and run a new A/B test every time. So you want an algorithm that can basically update, and if you lower epsilon to 0, you'll stop exploring. So here's an example where we're using what's called contextual bandits. So sometimes you don't want to just count things, you want to have a model for the values. So maybe if it's click ads, you have banner size and color, and you can have 1,000 different features for each ad, and you can model the click rates based on those. So this is just showing, this is a toy example that I did, but you know, for this dynamic thing where you can see the values of the arms are going positive and negative, and what's the best once is the worst later, you'll get basically 0 rewards on average if you don't account for this. But if you have a constantly dynamically updating estimate, you can do much better. So the red dots up here is showing what arm is being pulled, so you can see it kind of changes its choice of which is the best arm continuously, which is how you manage to have the red dots be higher up on these curves. Okay, so I don't think we have time to talk about this. I'll just say briefly, in general, so backing up away from multi-arm bandits, if you're talking about general reinforcement learning, you can apply it to anything that can be described as a Markov decision process. So here I've defined that. Read up more on it. There's a few different ways to solve these problems. Let's look at another example though, and then since in the interest of time. So Blackjack this is another example from the book Sutton and Bartow. Blackjack is a perfect example for a Markov decision process. Markov decision process just basically means the best action that you take in a given state doesn't depend at all on how you got into that state. It doesn't depend on the history. Okay, so in Blackjack, you have your hand, which is just a sum of the values of the cards you're holding, and you want to get as close to 21 as you can without going over. So when you decide whether or not to take another card, it doesn't matter how you got to your current value. It just matters what the total is. So this is a Markov decision process. So basically, your policy in this reinforcement learning problem is for any given hand that you're holding, should you hit or should you stay? So I did this, and I don't have the code here, but other people, you can find it online actually. This is because it's in Sutton and Bartow, a lot of people have worked through this. And this is the answer you come up with. So there's the x-axis is the total that the card that the dealer is showing. The y-axis is the total value of your hand. And then there's a yellow X everywhere where you should hit, and there's no X everywhere where you should stay. The reason there's two things is because it depends on whether or not you're holding an ace. So you can take this to Vegas. So maybe not, this is actually a simplified version because there's splitting and things like that, but this is the correct policy for this version of Blackjack at least. And then the colors correspond to the expected reward. So the way we set up rewards in this example is you get a +1 if you win, -1 if you lose, 0 for a draw. So everywhere it's dark red, you're very likely to win. Everywhere it's dark blue, you're very likely to lose. So you can get a sense of your chance of winning and decide how to bet according to this plot as well. We talked about mazes a little bit, but here's the output of actually running a reinforcement learning algorithm on a very simple maze. So here you get a reward when you reach the white circle at the end. So basically what you do is you just have the AI run this maze many, many times where you start it in some random position. It decides whether to go up, down, left, or right. And then based on the rewards that it ultimately receives, it learns the best direction to go. So the yellow arrows I've drawn an arrow in the direction of the maximum expected ultimate reward. And this is after running the maze thousands of times. Okay? So as you can see, it is obviously correct for this simple maze. We have a few more minutes?
Yeah.
Okay. So here's another example, which is maybe a little bit more practical from a business point of view. So I mentioned the IBM tax thing. If you look at that paper, it's actually kind of difficult to read because it's very complicated. There's many different things that you can do to try and collect taxes from people. So here's a very simplified version of that. Let's say you have somebody owes you $40, and every person will pay if you ask them some number theta times, and each person has their own value for theta, and theta is somewhere between 0 and 100. And let's imagine it costs you $1 to ask, right? So if you don't know a priori the distribution of thetas in the population, then it's hard to come up with a strategy for this. One naive strategy might be, well, we'll just never ask more than 40 times, right? Because that's kind of our break-even point. But if you use a reinforcement learning approach, let's take a kind of example that I put here. So the red curve is an imaginary distribution for theta, where there's some people who are relatively willing to pay. They'll pay after you ask them about 20 times. Others who need to be asked about 80 times, right? So over time, you could learn a sort of more nuanced strategy which is shown in the blue curve on the right, where your expected reward is positive up until about 25 times, because that's, yes. That's about how long it takes to be confident that the person is not in the first group, right? So if they haven't paid yet, then it's very likely that they are in the second group. So after about 25 times, you should just stop, because your expected rewards become negative after that. So you don't need to go all the way to 40. But then what this is telling us is, if for whatever reason you didn't stop, then you get later on, after about 40 actually, you now re-enter positive future rewards. So this is future rewards. This doesn't count we've already lost. So you'll still have negative money in the end, but what you're seeing here is, if you stupidly played this game this long, you better keep going now, because you want to collect money from the group in this 80 category. So you can get much more nuanced strategies this way than just simple break-even calculations. Let's see. Let me skip to some more examples real quick, and then we can go to questions. Okay, and Michael's reminding me there's a QA button that you can use on the left-hand panel to ask any other questions that come up. But I just want to show these real quick, just to give you some context, so you know this isn't just me talking about something obscure. So there's a paper by Yahoo Labs where they used a contextual multi-arm bandit approach for their news article recommendations. So basically, they have a bunch of features for each user based on their kind of prior behavior, et cetera, and other. I'm not sure what all the features are, but using this, they came up with a algorithm that worked well for recommending articles that people would click on. We already talked about tax collection a little bit. And then actually this Thompson sampling approach that I mentioned for the strategy for multi-arm bandits. Also, it's the randomized probability matching. So this is the engine behind some of the Google Analytics content experiments. So if you use Google Analytics for your own personal web page, and you want to, like, their version of A/B testing uses multi-arm bandits under the hood. So I think, especially for those of you who are interested in ad tech, definitely look into multi-arm bandits, but also I think reinforcement learning in general is something that is definitely worth everyone's time to dig into a bit. So should we switch to questions? Okay.
Headset.
Yes.
Are you still showing? Actually. Okay. All right. So I just want to ask the first question really quickly. Sure. So as a former fellow, what do you think is the biggest thing you got out of the program? So I'm going to ask you that, and also encourage folks who want to ask questions online to submit them on the Q&A.
Sure. So for me, I think that this is kind of a boring answer because I think this is what most people say, but that's because it's really true. The most valuable thing for me, coming fresh out of academia and not having a great grasp on the landscape of how data science exists in the business world, was just the chance to meet so many different employers, potential employers, both in person, but also just hearing about them from Michael and from the rest of the people here in the Data Incubator. It's a really, really efficient crash course in what the field of data science looks like. And, you know, I'm working at Capital One now, and they were not on my radar before I started Data Incubator. I didn't know that a job like this existed, or that it'd be something I'd be interested in. And you know, I'm very grateful that worked out, of course. But also, I would say that the coursework was very useful for me. I think that every person is different in terms of what their background is and that sort of thing. For me, I think I was an ideal candidate for it because I had a relatively strong technical background, and I was sort of ready to learn the material, but it was a lot of things that I hadn't been previously exposed to. So I think that I did learn a tremendous amount in a short period of time. So that was great also.
Okay, just to ask another question. So I think you said that Capital One was not on your radar when you started. I'd love to know sort of maybe what were your thoughts about what Capital One would have been like before you joined, or at least interviewed, and then kind of how have you, well, what did you learn through the interview process from meeting them, and now that you are an actual employee there?
So I think in my mind before, when I just sort of had this general notion that there was this world of finance and there was a world of data science, and there's some intersection, but there were kind of two different routes that one could take, and I felt more compelled towards data science. So I just wasn't really thinking about banks. And then what I found when I got to know Capital One is that there's this whole world of fintech now, which I guess you could say my job kind of falls into. But you know, things that have nothing to do with Wall Street and predicting the movement of stocks and things like that, but there's just a lot of room to apply data science and modeling in banking, or you know, banking adjacent products. There's just a very exploding field right now, I think, and there's a lot of opportunities there. So I'm glad that I found that out. And you know, I learned about Capital One specifically when someone from Capital One Labs came to Data Incubator, and I got to talk to him in person and that sort of thing. So it definitely,
the future boss.
Yes, exactly. So things still happen in kind of an old-fashioned way in some sense. Like I wish that there was like this efficient way that you could just learn about all opportunities that exist out there, but you definitely learn better about places where you actually get to meet somebody and talk to them one-on-one. So that was how it happened for me.
Okay, and for those of you who are wondering why you aren't able to pose a question, it sounds like what you'll need to do is refresh the YouTube page, and you should see a link to a Google Plus event. And apparently you can only pose questions through the Google Plus event. So I would encourage you to do that while you're at it. That should now, I think that was set up earlier, but if you're having some trouble accessing it, please please just do that, and we should be able to see your questions. Last question for you, Brian. So in terms of technical things, I'd love to understand a little bit more about the kind of the technical stack that you guys use. Are you a Pandas shop, a Python shop, a Scala shop? And then, you know, which tools you think were the most, which tools that you learned on at the Data Incubator were sort of most useful for translating into your work?
Okay. So I would say that we're definitely Python shop in general. And I use Pandas as well. I think a lot of people do. So Capital One has kind of gone all in. But like, I think they just sort of made a decision at one point, like, we want, for uniformity's sake, we're going to push everyone to go in the direction of Python. So Capital One Labs is a little bit different from the rest of the company in the sense that we're kind of expected to be a little bit more on the forefront. So that wasn't a very tough sell for us. But company-wide, there's a lot of people who've been around longer who are sort of statisticians who are now being rebranded as data scientists. And they're kind of having to move from older tools like SAS and things like that to Python. But there's definitely a strong push to do that. So I don't think in general every place is going to demand that you use Python, but in my experience, that's a safe route to take. And then, so there's also, so we're currently undergoing a push to the cloud, to AWS. So in the past, we had our own massive servers and databases, and that transition is still ongoing. It's a little bit difficult in banking, I think, compared to other places because there's so many security issues and everything needs to be kind of locked down. There's a lot of technical hurdles to deal with there. But definitely AWS is, I think, it'll never hurt you to learn your way around AWS. And when I first started, I was using, there's a pipeline tool that was developed at Spotify called Luigi, and we're using that to run MapReduce tasks. It's kind of similar to MR jobs that you guys use. But now definitely people are moving on to Spark, I would say. So, which intimidated me a little bit at first because I don't know, somehow I just had the impression that it was harder, but I think it's actually better in a lot of ways. So if you want to learn Spark, I think I would recommend that as well.
Spark or PySpark?
Well, that's a good question, actually. Just because I'm sort of more comfortable with Python and maybe I'm lazy, I've been using PySpark and I have not taken the leap into Scala yet. But there are definitely people who advocate for learning Scala. I'm probably not the best person to ask on that topic, but I think you can go in a direction there. Yeah.
Cool. No, thank you. That's wonderful. And it's also interesting to see this sort of transition of technologies. When I first started at Foursquare, we were using this thing called Uzi. I forget who used that. Mm-hmm. And then the cool new tool was Luigi. And so Luigi is sort of a Python DSL that can be used to wrap anything, usually kind of JVM MapReduce. Mm-hmm. And before that, I think Uzi was a Scala-based DSL that would do this that functioned the same way, but was a bit more clunky. And so we were very excited to be moving on to this newer, better technology from Spotify. Yeah. And now I think the industries are kind of already moved on, and we're sort of seeing a greater adoption of Spark. So it's been really exciting to see all these technologies as they've evolved, matured, been replaced with other technologies, and it's a constantly changing ecosystem. So we'll be interested to see what's happening next. But so anyways, thank you so much everyone who's sort of stayed around. Unfortunately, we weren't able to get, I think, the Q&A working because we haven't been able to receive anyone. We'll make sure to fix this for next time we do a DS30 because this has always worked before, and for some reason it hasn't quite worked now. But thank you so much for sticking around. If you're interested in applying for the Data Incubator, our application is currently open, and I think the deadline is for early applications is in about a week or two. So keep your eye out there, and I think Brian's notebook is actually publicly up on
That's correct.
GitHub. Is it on the Data Incubator's GitHub or your own GitHub?
Christian forked it into Data.
Okay, it's in the Data Incubator's GitHub. So if you go to or if you search for GitHub, the Data Incubator, you'll find our GitHub, and this should be one of the public repos there. And I'll make sure to also just add a quick link to our application there so that you guys have access to that. And I'll also make sure to cross-link the YouTube page where this Data Science in 30 Minutes will ultimately go with the GitHub and vice versa. So thanks everyone for joining us today, and I hope you have a wonderful day.
All right, thank you.